Start by understanding the core concept of a linked list. A linked list is a linear collection of data elements called nodes, where the order is determined by pointers rather than physical placement in memory. Each node is split into two parts. The first part holds the actual data, and the second part, known as the link or next pointer, contains the address of the next node. The final node points to a special value called the null pointer, marking the end of the list. If there are no nodes, we call it an empty or null list. This structure allows for dynamic memory allocation and flexible data management, making linked lists a fundamental concept in computer science. Now let's see how linked lists are represented in memory. Typically, two arrays, info and link, are used. Info holds the data for each node, while link stores the address of the next node. A variable, often called start, points to the first node, and a special value null indicates the end. Importantly, nodes do not need to be stored in adjacent memory locations, allowing for efficient use of memory. Multiple lists can share the same arrays, but each must have its own start pointer. This flexibility is one of the reasons linked lists are so powerful for dynamic data storage. Implement linked lists in C. We use structures to define nodes. Each node contains a data field and a pointer to the next node. Memory for new nodes is allocated using the malloc function, and nodes are removed with the free function. For example, a node can be defined with a struct containing a character array for data and a pointer to the next node. Creating a new list starts with setting the pointer to null, and new nodes are added dynamically as needed. This approach enables efficient and flexible list management in C programming. Managing memory efficiently is crucial for linked lists. When nodes are inserted or deleted, we need a way to track available memory. This is done using a free storage list, also called the free pool, which keeps a list of unused memory cells. When a node is deleted, its memory is returned to the free pool, making it available for future insertions. This system ensures that memory is reused efficiently, preventing leaks and optimizing performance, especially in programs that frequently modify linked lists. Garbage collection is the process of reclaiming memory from deleted nodes. The operating system may periodically collect all unused memory and add it back to the free pool. This process is essential when memory is limited or when the system is idle. Overflow occurs when there is no available memory to insert new nodes, often handled by displaying an overflow message or expanding the memory pool. Efficient garbage collection and overflow handling are key to robust linked list operation. Underflow happens when you try to delete a node from an empty list. In this situation, the program typically prints an underflow message. Underflow is detected when the start pointer is null and a deletion is attempted. Handling underflow properly prevents errors and ensures the stability of your program. It's a basic but important part of managing linked lists, especially in applications where frequent deletions occur. Traversing means visiting each node in the linked list to process its data. This is done using a pointer variable, usually called PTR, which starts at the first node and moves through the list by following the link field. The process continues until PTR becomes null, indicating the end of the list. Traversal is fundamental for operations like printing, searching, or modifying the list, and is the basis for many linked list algorithms. Searching involves finding a node with a specific value. For unsorted lists, you traverse each node and compare its data with the target value. If the list is sorted, you can stop searching once the current node's value exceeds the target. The search returns the location of the node if found, or null if not. The efficiency of searching depends on the list size and whether it's sorted, but in general, it's a linear operation. Insertion in linked lists can occur at the beginning, after a specific node, or into a sorted list. When inserting, you adjust the pointer so the new node fits seamlessly into the list. If inserting at the start, the new node points to the former first node and start is updated. For sorted lists, you first find the correct position, then insert. Memory for the new node is taken from the free pool, ensuring efficient use of resources. There are two special cases in insertion. If the new node is the first in the list, the start pointer is updated to point to it. If the new node is the last, its link field is set to null. These cases ensure the list remains properly linked, regardless of where the new node is inserted. Handling these scenarios correctly is essential for maintaining the integrity of the linked list. Deleting a node involves adjusting pointers so the node is removed from the list, and its memory is returned to the free pool. If deleting the first node, start is updated to the next node. For other nodes, the previous node's link is updated to skip the deleted node. This process ensures the list remains connected and memory is efficiently managed. Deletion is a common operation, especially in dynamic data structures. Doubly linked list allows traversal in both directions. Each node contains three fields: the data, a pointer to the next node, and a pointer to the previous node. This structure makes certain operations like deletion and backward traversal more efficient. Insertion and deletion are straightforward, as you only need to update the neighboring node's pointers. Doubly linked lists are especially useful when you need to move both forward and backward through data. Header linked lists include a special header node at the start. There are two main types: grounded header lists, where the last node points to null, and circular header lists, where the last node points back to the header. Circular lists eliminate the need for null pointers and ensure every node has a predecessor. These variations provide additional flexibility and can simplify certain algorithms, such as traversing or inserting nodes. Stacks and queues can be efficiently implemented using linked lists. In a stack, nodes are added and removed from the top, following the last in first out LIFO principle. In a queue, nodes are added at the rear and removed from the front, following first in first out FIFO. Linked implementations allow for dynamic resizing and efficient memory use, making them ideal for applications where the number of elements changes frequently. Linked lists are used to represent polynomials, where each node contains a coefficient and exponent. Adding two polynomials involves traversing both lists, comparing exponents, and creating new nodes for the result. This approach allows for efficient storage and manipulation of polynomials, especially when many terms are zero. The algorithm for polynomial addition is optimal, with a time complexity proportional to the sum of the number of terms in both polynomial. Sparse matrices, which contain mostly zero values, can be efficiently represented using linked lists. Each non-zero element is stored in a node, and header nodes are used for rows and columns. This structure saves memory and speeds up operations by only storing and processing non-zero elements. The linked representation is especially useful in scientific computing and large-scale data analysis, where matrices can be very large but sparse.